All right. Good morning, everyone. So same thing here. The camera's not working, so I'm going to go ahead and just narrate over the slides, and then um, hopefully it worked for you yesterday. If not, let me know, and then I'll try to work on the camera issue. But right now, let's continue on with. Let me go ahead and I'm sorry, let me go and start the timer here first. Let's go ahead and let's continue on with where we left off with yesterday. And so yesterday, you were asked, and we went through it to describe the molecules. So, given a molecule, you'll need to be able to describe it. And in your description, then make sure you remember. Then you need to make sure you include the bond. Okay, what type of bonds holds the atoms together? The hybridization. That is, how is the central atom hybridized? And I want to make sure I'm clear on this. When we talk about hybridization, we're talking about the hybridization of the central atom. And the central atom, remember, is the atom to which all of the other atoms are attached. And you will find in certain molecules that there's more than one center atom. But for our purposes here, what I will do then is I will specify for you which atom you'll need to describe the hybridization for. Okay, so make sure you keep that in mind, that you need to be able to describe the type of bond that holds the atoms together, the hybridization of the center atom, and how that hybridization is able to hold the molecule together. And then we need to make sure that we discuss then the bonding interactions as well, and that's the sigma and pi bonding interactions that we talked about in class and in lecture. Okay. And then finally, what we'll be discussing today then is we'll be talking about the geometry, and I introduced that to you yesterday, and that is we'll talk about the geometry of the molecule as well. And the geometry also is when we refer to the geometry of a molecule, it's also around the center atom. So it's the center atom. Again, the center atom is the atom to which all other atoms are attached. It's the center atom that we'll use to describe the hybridization of the molecule, and also the center atom which we'll use to describe the geometry of the molecule. And so yesterday we saw then with methane, which is CH4, we saw then that methane, when I was asked you to describe it, we said then that methane, all four bonds that holds those five atoms together are single bonds. As a result, then the center atom, in this case, which is the carbon atom, is sp3 hybridized. The hydrogens, remember, are not hybridized at all. We have this they are unhybridized s orbitals, and so the alignment of the hydrogen with the carbon is going to be then a sigma bonding interaction, okay, because they align in such a manner where when they overlap, we can draw a straight line through that interaction, and so we call that a sigma bonding interaction. And so with that said, then we were able to take a look at methane, and we were able to show, we will be able to show at the end of the lesson today, that methane, the geometry around, again, the carbon atom, which is the center atom, is going to be tetrahedral in the electron geometry, and tetrahedral also with the molecular geometry. Okay, with ammonia, which is NH3, we saw them with that particular molecule. There are three single bonds that holds the hydrogens, all three hydrogens to the nitrogen. And so we saw them with that particular molecule. The nitrogen in this case, which in this case is the central atom, is going to be sp3 hybridized. Okay, the hydrogens again do not hybridize, so it's an s orbital. And so the overlap between the s orbital from each hydrogen with the sp3 orbitals from the nitrogen also is going to create a sigma bonding interaction that holds those three atoms together. And then we saw then that the shape then around the geometry around the nitrogen atom is also going to be tetrahedral when we discuss the electron geometry, but it is trigonal planar, trigonal pyramidal when we talk about the molecular geometry. So if you're a bit confused about what the difference is between the electron geometry and molecular geometry, look, we'll discuss it today, but you had a chance to take a look at that when you did the PhET lab on Thursday of last week. Okay, and so with that said, then don't worry if you are still a little bit concerned about what those terms mean, what the molecular geometry means, what electron geometry means. We'll go over that today, and I'm going to use your PhET lab also to help you with that. Okay. All right. So what I would like you to do, and just a chance to practice this a little bit more. Let me go ahead and open up the whiteboard here for you. What I'd like you to do then is I would like you to describe the molecule that I'm going to give you here. So I want you to go ahead and describe this molecule here that has the formula C2H4, sorry, C2H4. Okay, this is what we refer to as ethene. The name of this one is ethene. That's the name that's given to a common name given to it. The systematic name then we would see that it's dicarbon tetrahydride. Okay, so go ahead then, and what I'd like you to do is take about 2 minutes to describe the molecule here. Now, make sure in your description you draw the correct Lewis dot structure for this molecule as well. And so once you get back then, let's make sure then that you have your drawing and your description in front of you. Try your best with the geometry, folks, but hopefully you can get at least the bond type, the bonding interactions, and also the hybridization for this molecule. Okay, so take about 2 minutes and draw the describe the ethene molecule. Okay. Okay. Hopefully you had a chance to draw. Hopefully you had a chance to do it. First thing you want to do in your description is to draw the structure. Okay, so carbon. Hopefully you were able to do this. Is double bonded to carbon. Okay, and each carbon then is going to be single bonded to the hydrogen. And if you've noticed by this point, then that every time a hydrogen is involved, okay, hydrogen is always attached to every other atom by a single bond, because that's only what it can do. So with that, with this molecule, then make sure you remember that. You can remember these little tricks here to help you out as well. Okay. All right. So with that said, if we notice here, let's start out with describing the types of bonds that hold these 6 atoms together, starting out with the single bonds. And like we pointed out, we have then 2 single bonds each. Okay, so we have a single bond here and a single bond here. Okay, we have 2 single bonds holding the hydrogens to attaching the hydrogens to the carbons. Okay, so we have 2 single bonds on both sides. I'm just going to focus on the left-hand side here. You can imagine then the right-hand side is repeated. So we're going to imagine then, and I'm going to call this C1, carbon number 1, and this carbon number 2. And you're going to see then that in reference to carbon number 1 as the center atom, we can say the exact same thing about carbon number 2 if we were to reference it. Okay, so I'm just going to go ahead and reference carbon number 1. We're going to describe this molecule based upon carbon number 1 here. Okay, all right. So we have then a single bond that holds each one of those hydrogens to the carbon C1, and we notice then that we also have a double bond that holds each carbon to each other, the 2 carbons together. So we have 1 double bond and 2 single bonds that holds these 3 atoms together. Okay, so the carbon, the 2 hydrogens, and the carbon here. Okay, so we're looking at C1 as the center atom right here. Okay, all right, so there it is. That's the description of the bonds. Okay, we have 2, and I should write here, we have 2 single bonds, okay, and 1 double bond. Okay, all right, now with the hybridization. The hybridization then is going to be based upon, and remember we talked about this, whether the atom has a single bond, double bond, or triple bond holding it to some other atom. The very fact that this carbon here has a double bond attached to it, that's all you need to make to identify the hybridization. Not the fact that these two hydrogens are single bonded to the carbon. That is important, okay, but it is the double bond here that determines the hybridization of that carbon. And so hopefully you were able to pick up on that distinction yesterday, and that is whenever an atom only has single bonds attached to it, that atom then is going to be sp3 hybridized. If that atom has at least 1 double bond shared with another atom, so if that particular atom has at least 1 double bond, you know then that atom is going to be sp2 hybridized. And if an atom shares a triple bond with another atom, okay, then that atom then is going to be sp hybridized. So look for the bonding type to help you determine the hybridization. Okay, so yes, we have single bonds here. So could this carbon be sp3 hybridized? It could, but if you look at the 3rd bond that this carbon here shares. Okay, it is a double bond, and it's that double bond right there that helps us then figure that this is an sp2 hybridized carbon. The carbon here is sp2 hybridized, which means then let me just go ahead and draw this for you. Okay, if you can imagine it, there's C1, and so with the sp2 hybridization, what we have then is we're going to have then 3 sp2 hybridized. 3 sp2. So each one of these here are sp2 hybrid orbitals. That's 1, 2, and there's 3. So there are the 3 sp2 hybrid orbitals. And remember, the last orbital for this particular atom then is an unhybridized p orbital. So let's go ahead and draw this here. So let's imagine then that this is on a plane. Unhybridized p orbital then will be above and then below the plane here. So this is an unhybridized p orbital here. And that's how you will imagine the carbon, the orbitals sitting around the carbon. And remember, what we have here then is an electron is going to be present in each one of these. Electron there, electron here, and electron here. There's going to be an electron in each one of the hybrid orbitals, and also an electron in the unhybridized p orbital as well. Okay. All right. So with that said, then that's sp2 hybridization around carbon number 1 here. So you can imagine then what happens is that the hydrogen, so each there's going to be one sp2 hybridized that's going hybridized orbital that's going to be bonding with the hydrogen atom here. So let's imagine then the hydrogen atom, which is, remember, an unhybridized s orbital. Okay, so you have then, and I'm going to draw this here real quickly. You can imagine then, and I'm sorry, let me move this to the side really quickly so I can show you this. Okay, so we have then a hydrogen atom. Our hydrogen atom moves in and it interacts right there. So there's our hydrogen atom, okay, with its 1 electron. And again, this is sp, so this is an sp2 hybrid orbital. This is an unhybridized s orbital here. Okay, and remember, the hydrogen here has its own electron. It has 1 electron there. And so there's the sharing. As soon as this sp2 hybrid orbital here overlaps with an unhybridized s orbital from the hydrogen here. So this is a hydrogen atom. Remember, this is the hydrogen atom right over here. And let's focus in on this single bond right here. Okay, so there is the sharing right there of 2 electrons. That is going to be a single bond. The overlap here, and again, you can draw a straight line through this this overlap right there, and it based on that, this bond here then is going to be what we refer to as a sigma bond. Okay, so this is going to be then a sigma bonding interaction, okay, between an s orbital from hydrogen and an sp2 orbital from the carbon. Okay, so let's go ahead and identify that. So this is a single bond here. And so that single bond then is going to be sigma. It's going to have a sigma bonding. Oops, sorry, sigma bonding interaction. All right. So that's what we have right there. Okay, so that's how we can explain the single bond. That's how we can explain the single bond. But what about this double bond right here? Okay, what about that double? Well, let's take a look at this. So let's go ahead, and that's carbon number 1. Here's carbon number 2. Carbon number 2 is going to be hybridized in exactly the same way. I'm sorry, let me go do this here. It's going to undergo the exact same hybridization as carbon number 1. So I'm going to draw carbon number 2 over here. So there's carbon number 2. It will also have 3 sp2 hybrid orbitals. So let's go ahead and draw that in. So we're going to have the 1, whoops, sorry. We're going to have the 1 sp2 hybrid orbital here. Come on, you. Okay. So there's 1. I'm going to stretch this out a little bit here. Okay, so there's 1 sp2 hybrid orbital. Here's a second sp2 hybrid orbital. And here's a third sp2 hybrid orbital. So you have 1, 2, and 3. So there are the 3 sp2 orbitals from the carbon, second carbon here. Okay. And then it also has an unhybridized p orbital. So they are identical to one another. So it has also an unhybridized p orbital above and below, sorry, for the plane. So this is an unhybridized p orbital. right here. Okay. And so in this case, then, just like with carbon number 1, carbon number 2 will have 1, 2, 3 electrons in the sp in the hybrid orbitals and 1 electron in the unhybridized p orbital. Now, you can imagine then this sp2 hybrid orbital and this one here. So these two over here will be bonded to the hydrogens here in a single bond. Okay, sigma bonding. Okay, sigma bonding interaction that'll hold those together. So the same thing over here, and maybe I'll just draw this over here for you, just to make sure you understand then that this bond over here, this orbital over here is also going to be interacting. And let me actually just draw this to the side really quickly. It will also be interacting with a hydrogen atom. So the hydrogen atom is going to come in. Okay, so that's the s orbital for the hydrogen atom. Okay, so unhybridized s orbital here. Oops, sorry. Okay, and so there's the second overlapping here, and we can again draw a straight line through this one. Okay, and so therefore this is also going to be a sigma bond as well. So this is sigma bonding interaction, and this is a sigma bonding interaction. You can imagine it being repeated over here with these two sp2 orbitals from carbon number 2, which leaves then this interaction here. Okay, what's going to happen then is that the sp2 hybrid orbital from carbon number 1, the remaining one, with the hybrid orbital from the sp2 hybrid orbital from carbon number 2 here, there's going to be an overlap, and I'm going to draw this here as a red overlap here. Okay, you're going to have this overlap between these two right here. That actually that doesn't look so good. Let me go ahead and erase that. Okay. Okay. What we're going to have then is that these two are going to get close enough together where they will overlap, and they will overlap in a linear manner there. So there's that overlap, the sharing of the 2 electrons there. Okay, and so therefore you're gonna be able to draw a straight line through that interaction there. So this interaction right here is a sigma bonding interaction. So you have a sigma bonding interaction here. Okay, sigma bonding interaction. All right. So these 2 electrons here, these 2 electrons sitting here in the sp2 hybrid orbitals, they're going to overlap in a linear manner. So therefore, that's a sigma bonding interaction. And then that leaves then these 2 electrons here in the p orbitals. Okay, these 2 electrons here in the p orbitals, what's going to happen then is that they will overlap in a side-by-side manner. If you notice here, these 2 orbitals here are going to overlap in a side-by-side manner. Okay, and so what we see, and I'm sorry, let me erase the bottom one. I just want to make sure you understand then that the bottom lobe here of the p orbital also will overlap in a side-by-side manner. And so therefore, if they overlap in a side-by-side manner, remember, this then becomes, this interaction here is going to be then what we call a pi bonding interaction. Okay. Okay. And so that's what makes the double bond. The double bond of the double bond, one of those double bonds will be sigma bonded. Okay, so you'll have one of those that will be sigma bonded as well. But the second of the two bonds, which I'm going to point to as up here, it will be, I'm sorry, let me go ahead and move this out a little bit. It's going to be pi bonding interaction. And that will always be true for a double bond, pi bonding interaction. So therefore, in a double bond, 2 of those electrons that form one of the pair, okay, will be sigma bonded together. They will share on a side-by-side manner. The second pair of the double bond, the second pair of electrons of the double bond, they will be lined up side by side instead of lengthwise, side by side with one another, and thus they have that pi bonding interaction. So in a double bond, you will always have one sigma bonding interaction and one pi bonding interaction. For a single bond, it will always be sigma bonding interaction. So you can imagine with the triple bond, which I won't talk about here. If you're interested in that, we can come by and talk about it. In a triple bond, you can imagine then it's going to be then at least one sigma bond, and hopefully you're going to start to see them, because remember, with a triple bond, it's going to be sp hybridized, okay, sp hybridized. So therefore, you're going to have one sp2, I'm sorry, sp hybridized orbital, and you're going to have two. I'm sorry, you're going to have two sp hybrid orbitals, and you're going to have two unhybridized p orbitals. Okay, and hopefully, as you'll see then, it's those p orbitals that will line up side by side, and therefore then you'll have two pi bonds in a triple bond, and two pi bonding interactions and one sigma bonding interaction. Okay. Now I know that this looks a bit messy here, but please do understand then that there is when you do this, you got to be able to identify the bonding interactions. Hopefully, you'll be able to do that with the single bonds and the double bonds. Again, I'm going to hold off on asking you about triple bonds, because we'll talk much more about that. For those of you folks who are going on, we'll talk much more about that in AP chemistry. Okay. All right. So that is it for the description. I'm sorry, and then geometry. I'm sorry, with the geometry. What we're going to see then is that you have 3 electron domains here. Okay, so let's go ahead and take a look at this then. Okay, we have 3 electron domains. Okay, electron domains then are regions of electron density. So we have 1 electron domain here. That's a bonding electron domain. Here's a second bonding domain here. And even though this is a double bond, it counts as 1 region of electron density. So therefore, it is a third bonding domain. And so whenever you have 3 bonding domains in, the geometry then, if we take a look at the geometry, okay, and let's take a look at the the electron geometry first. Okay, so whenever you have 3 electron domains there, it will always be trigonal planar. It will always be a trigonal planar electron geometry. Here, because you have 3 bonding domains and no lone pairs, which are non-bonding domains, the molecular geometry, okay, will also be trigonal planar. And hopefully you noticed that in the very first part of the PhET lab that I think it was question number 4, where you had to make a molecule with only bonded, okay, single bonds. You saw then that the electron geometry and the molecular geometry exactly coincided with one another. Okay, so that's what we have right there with the electron geometry and the molecular geometry. So this is how you complete the description of this particular molecule. A little bit more involved than what we did yesterday. The diagram on the right, where I drew for you the hybrid orbitals, I wouldn't worry about that. I'm not going to ask you to draw that on the exam. What I will ask you to do is do what I showed you on the left, the diagram on the left, where I draw the Lewis dot structure. I label all the bonds, I label the bonding interactions, and I provide the geometry. You got to be able to do all of that for the exam once we get back for the exam for this chapter. Okay, so please make sure you keep that in mind, and then if you have any questions, please come ask. What I'll try to do then is I will try to put together, again, your book doesn't do a very good job of providing you practice with this. It doesn't really go into detail, very much detail about the bonding interactions and describing the molecules, and it talks a little bit about the geometry. It only focuses basically on the molecular geometry. It doesn't talk very much about the electron geometry. It doesn't talk at all about the electron domains. And so, like I said, that's why I supplement what we do here in class with the PhET labs and these other things to give you a slightly broader picture than what's provided for you in the text. Okay, so that's why I make sure then that if you have any questions about the PhET lab, you come by and you ask me as well, because that PhET lab will be important in your overall understanding of what we were talking about here. Okay. All right, very good. So let's go ahead then, and let me clear this out here. Okay, and let's go back to the lecture slides then. Okay, so describing the molecules, you got to make sure you understand that. Okay, so let's talk about the geometry then. I've been talking about geometry quite a bit. Okay, and so let's provide a clear understanding and define why molecules assume the shapes that they do. And we're talking about 3-dimensional shape here, guys. So when we talk about the geometry of a molecule, okay, what we are discussing then is we're discussing the 3-dimensional, okay, we're discussing the 3-dimensional structure of a molecule. We live in a 3-dimensional world, so do the molecules. We are three-dimensional entities, and so too are the molecules. However, the reason why these molecules assume a three-dimensional shape is slightly different from how we assume a three-dimensional shape. The three-dimensional shape of a molecule is based on one very simple fact, and that is electrons repel one another. And so that means then if the bonds, these covalent bonds are electrons, they are shared electrons, remember, then that means they repel each other. And so the repulsion of electron pairs, either bonding or non-bonding. Okay, so when we talk about the electron pair here, this electron pair here is going to be both defined then as bonding, and I'm going to go ahead and I'm going to clarify this here. Okay, so when we talk about electron pairs here, we are describing both the bonding. I'm going to do this here. So we're describing bonds. So we refer to those as bonding pairs. Okay, and also lone pairs. Okay, so lone pairs and bonding pairs, they are made up of electrons. Okay, so the electron pairs here, okay, are classified then as either bonding or lone pairs, what we refer to electron pairs, or what we refer to as non-bonding pairs as well. So I use both terms interchangeably. Okay, so lone pairs or non-bonding pairs as well. Okay, so when you have these electron pairs, they will repel one another. They don't like being next to each other, so they're going to try to push out away from each other as far as possible. And so that's how we can explain the three-dimensional structure of a molecule. So the theory that explains it, or the idea behind it, is what we refer to as the valence shell electron pair repulsion. Valence shell because it's the valence electron pairs, it's the valence electrons that are involved in bonding, and it's the electron pairs in that outermost shell that repel each other and is responsible for the three-dimensional structure. Okay, so the valence, and we refer to this then also, I refer to it in short, and a lot of folks do as well, as VSEPR theory. Okay, so it's going to be VSEPR, or VSEPR theory. So this VSEPR theory helps us to explain. So how is it described in words? Okay, let's go ahead then. Let me give you the definition of VSEPR theory. So that's it right there, and I talked about that. So it's repulsion of electron pairs, and what I would like to you to understand is that when we talk about electron pairs, okay, the term that's used also quite a bit is what we refer to as electron domains. Okay, so these electron domains, okay, so electron pairs here, what we also refer to as the electron domains. And your PhET lab also refers to these as electron domains. Now, with the one caveat here, and that is when we talk about electron domains, we're talking about regions of electron density. Okay, regions of electron density. So therefore, we count lone pairs and bonding pairs as well. Now, the bonding pairs we don't differentiate when we talk about these electron domains. So therefore, single bonds, double bonds, and triple bonds count as a single electron domain. So a single bond is not one electron domain, and a double bond is two. Okay, a single bond and a double bond count as one region of electrons. So therefore, we refer to it as electron domains. Okay, and so electron domains repel one another. So that's what we want to make sure we keep in mind as we go through this. Okay, so let's go ahead then, and what I'd like to do then is to help you understand what this geometry means. Let's go ahead and let's take a look at the PhET lab. Okay, so let me go ahead then, and the little time that I have left here, let me see how much time I have left here. Okay, yeah, let's take a look at the PhET lab, and let's see how electron pairs repel one another. Okay, all right, so this should be familiar to you. Oh, let me go ahead. What happened here? I had it loaded, ready to go. Okay, let me see. All right, there it is. It's starting up again. Okay. All right, so when we talk about electron repulsion, let's see it's kind of a little bit slow here starting up. Hopefully the PhET lab you were able to, okay, so let me, first thing is, let's start out with the models here, the model, okay, and I'm gonna go ahead and remove the bonds here. So if you notice, what they do is they give us the option, and I'm gonna make this a full screen here. Let me do this. Okay. So what they do here for us then is they give us these bonding electrons here. So if you notice, we have single bond, double bond, and triple bond. Make sure you understand then what we have here. Whoops. There it is. Okay, so these are what we refer to. So the electron domains are here. So we have bonding electron domains and non-bonding electron domains here. So these are the non-bonding here, and these are the bonding. Whoops, sorry. These are the bonding. Okay, and these are the electron domains that we will be referring to. So we have bonding electron domains, which can be classified then as a single bond, a double bond, or triple bond. Okay, so single bond, then a double bond, triple bond, they all count as a region of electron. And so when we talk about a repulsion, they repel basically the same way, though some folks in the past have asked them, but wait a second, how is it that a single bond repels as much as a double bond when a double bond is made up of 4 electrons and a single bond is made up of 2? Well, it does. And so we can talk about this a little bit later. It's best then for right now, for right now, make sure you keep in mind then that when we talk about the bonding domains, we treat single bond, double bond, triple bond as a single bonding domain. They're not separate. It's not one bonding domain here, and we have 2 bonding domains here, 3 bonding domains for the triple bond. Each one of these bonds count as a single electron domain. So the lone pairs then represent the non-bonding electron domains. Okay, so that's what you want to make sure you keep in mind as we go through this, because they will repel in the same way. Okay. All right, so with that said, hopefully you go down here and during your lab, then I think I pointed out to you, make sure then you choose the option for molecule, molecular geometry, and electron geometry as well, and be able to tell the difference between those two. Okay, and so when we talk about this, then let's take a look then what happens when we include a single bond right there. Okay, so we have a single bond. So our center atom here is our purple atom here. Okay, so as soon as you put in that center atom, then as soon as you attach a single bond to that center atom, look at the molecular and linear electron geometry. The electron geometry, and let's make sure, and let me clarify this for you. Okay, the electron geometry here, oops, let me go ahead and, okay, the electron geometry here takes into account all electron domains. So when we talk about how they repel each other, we're counting all electron domains. Okay? With the molecular geometry, we are only taking into account then bonding. The name then is only going to take into account the bonding electron. Electron domains. And that's the key difference. Okay. Now, a lot of times, the molecular geometry and the electron geometry are exactly the same because you don't have any non-bonding electron domains here. So if you take a look at this very first, our generic molecule here of a single bond of one atom, single bonded attached to a center atom here, then therefore, with that said, then this molecule is comprised only of electron domains, and therefore, bonding domains. So therefore, then that's when the molecular geometry and electron geometry, they overlap. They are exactly the same. They will have the same name, and this will occur when a molecule only has bonding electron domains, that there are no non-bonding electron domains. That means there are no lone pairs. Okay, right. So with that said, then it's linear, because if you notice here, then the angle here, and I'm sorry, let me go ahead and show the bond angle here as well. We should click that on. The bond angle then is, I'm sorry, well, they're not going to show this one, but it's 180 degrees, because you have 180 degrees when you have a single bond here. Now, what I want to point out to you then is you're going to see then that this same molecular and electron geometry will be, we'll see that if we were to attach a double bond. And that's what I'm trying to tell you. The double bond, the single bond, the triple bond only they count for a single electron domain. And so therefore you will get the same geometry there. So if we have a single bond, you have attached to the center atom here, we have a linear geometry in both the molecular and the electronic sense. If we have a double bond, again, we have a linear geometry for the molecule and the electron as well. And then finally, just to show you then that this is correct, if we add in a triple bond, same thing again, the geometries are exactly the same for both molecular and electron. Okay, so the bonding electron domains, it doesn't matter that we don't differentiate between the single, the double, and the triple. They all count as one bonding domain. Okay, that's a single type of bonding domain. Okay. All right. So with that said, then let's take a look at what happens when we add 2. Okay. So there is the angle right there. So if we add in 2, and let's go ahead, I'm going to just turn this around for you guys to see here. Okay. And the cool thing about this FetLab here is that it's a 3-dimensional FetLab, so you can turn this around. Okay. All right. We add in a second bonding domain. Okay. So we add in a second bonding domain here. So we have 2 single bonds. Remember, each one of these bonds here is comprised of 2 electrons each. So what do? They want to repel. They don't want to be next to each other. And so they want to get as far away from each other as possible. And the only way they can do that is to be on opposite sides of the center atom. Okay. And so when you have 2 single bonds here, the furthest they will get away from each other is by being on opposite sides of the center atom. And so therefore the angle between them will be 180 degrees. But if you notice here, we have then a linear geometry for both the molecular and electron geometry. Okay. Now I'm going to go ahead and I'm going to replace one of those single bonds with a double bond. And sure enough, what do you notice happening? Again, we assume a linear geometry. Okay, the double bond doesn't repel more than the single bond. Okay, it repels the same. And so therefore, again, to get farthest away from each other, these 4 electrons here on the left-hand side from the double bond was going to push away from the 2 electrons here on the right-hand side from the single bond, so that we also form a 180-degree angle as well. And again, I'm going to go ahead and add in a triple bond. And again, we see then that the furthest that they can get away from each other is again 180 degrees. So when we talk about repulsion, when we talk about electron repulsion, the single bonds, the double bonds, and the triple bonds will repel each other in exactly the same way. So these 6 electrons here don't repel more in the sense than the 2 electrons here. So the furthest that the triple bond can get away from the single bond is again across an angle of 180 degrees from this center atom here. And so you notice then changing the electron domains, changing the bonding electron domains, okay, we still count each electron domain, each type of bond as a single electron domain. So for the center atom then, we have 2 different electron domains. We have a triple bond electron domain, and we have a single bond electron domain. Okay, again, the triple bond here does not count as 3 separate domains. Okay, it has 3 bonds here, but each bond does not count as a single electron domain. The triple bond as a single entity counts as 1 electron domain. Okay, all right. What I would like to do then is I'm going to go ahead then and we will pick up with this discussion after a break. I think over break, if you could, I think the best thing for you to do to kind of keep this fresh in your mind is, right before we get back from vacation, take a look at your FetLab and kind of play around with it again a little bit more. See if you can familiarize with this yourself, refamiliarize yourself, reacquaint yourself with the terms here, and also with what happens with these bonds. And that way, then when we meet again after break, I can just pick up with this and then finish up this discussion and move on. Okay. All right. So with that said, folks, have a great vacation. Have a happy Easter, and I will see you folks. Actually, hopefully, I will see a few of you folks in person at school once the break comes. Once we get back from the break. But for everyone, have a happy Easter, folks, and I will see you back in school, whether it's in Zoom or back physically in school after the vacation. Okay. Have a good vacation, folks, and I will see you in about a week or so. Okay. All right. Bye.